Okay. Another concept that, again, you might say, what is the point of knowing this? It's to understand some of the inner workings of what your soil does, so that when you say, why is it reacting this way when I do this? Or why isn't my pH changing? On and on. You have kind of the building blocks to logically put it together and have a better understanding of why it's doing what it's doing. So when we take a soil sample, and we'll talk about that, your report's going to come back with a lot of different things. And one of them is going to be a cation exchange capacity, or CEC. A cation, and I know we have at least one chemist viewing today, is a positively charged ion, which would be most of the nutrients that we rely on for plant nutrition. So if you think about calcium, magnesium, potassium, ammonium, there's a lot of these nutrients, zinc, iron, a lot of these nutrients have a positive charge to them. Now, why does that matter? Well, if nutrients were like water, every time you'd fertilize your soil, they would just leak out the bottom, right? When we get excess rain, that rain either runs off or it goes and disappears into the soil profile. You rarely get to capture all that water and use it unless you have space in there. But fortunately, soil has the ability to electrically hold on to those nutrients, which makes managing it from a fertility standpoint much easier, much better to do. And that's because soil particles, in specifically your clay, not your sand, not your silt, clay particles only, are weathered to the point where there's these chemical, there's this, I guess they call it valence on the shell of the clay particle, which allows for these negative charges. And so in a sense, clay is negatively charged. Opposites attract. And so those positive nutrients like calcium, potassium, so on, are attracted to that particle and are loosely held. Okay, so what this looks like, and I promise you there's a purpose of why I'm showing you this. It's not like a magnet, like you would think, like things just get sucked together and they're held really tightly. It's not a covalent bond. It's not like that. It's a loose association. Soil is a particle, but there's what's called the soil solution. It's this kind of fluid part right outside the particle, and fluid implies there's water there. And that's where the nutrients are. And so if I could draw it out, keep having these little glitchy spikes. I'm not sure what's going on there, but I'm just going to draw them as little circles. And they're attracted to the different charges of the soil. Now, if I was going to draw what they were, I'd say they balance the charge out. So hydrogen is +1. So it would need 1 minus to attract it, so to speak. I'm oversimplifying, but I'm doing this on purpose. So here's another hydrogen. Let's put a calcium, which is 2 positive. Let's put another hydrogen, which is 1 positive. Let's put a magnesium, which is 2 positive. Your soils, for the most part, are going to have a ton of calcium and magnesium in the soil. Now, if you have a really acidic soil, it's going to have a lot of these hydrogen. Okay? Why this matters? Because they're associated with this loose fashion. They call this the diffuse layer, meaning it kind of diminishes as it gets further away from the particle. So there's this urge, so to speak, for these particles to be attracted over here to the negative, and they're all positive. And so it kind of aggregates as close as it can to the surface, but then all these other cations are trying to vie and box for position because they're moving. They're constantly moving in solution. And that gives us an opportunity to correct some situations, which we're going to talk about as we go on. But it also poses some challenges when we do want to manage, because the amount of negative charge, which is based on what I said is CEC, determines this process. And the amount of CEC is determined by how much clay you have in your soil. Clay, or I should say organic matter, composted organic matter. Okay, we'll come back to this. Now, I said cations, positive charge. What about the negative ions that we need? Plants take up a lot of other nutrients besides the ones I mentioned. You take up phosphorus, and it takes up phosphorus, which is a negative compound. It takes up nitrogen as ammonium, but it also takes it up as nitrate, which is negative. Now, if soil's negatively charged, this is a question out to everybody. What's going to happen if I try to store that nitrogen in the soil? What's going to happen to it over time as we get more rain, as it just sits there? Is it going to stay in the soil? Is it going to leave the soil? What do you think is going to happen? Your soil's negative, nitrate's negative. So I'm going to wait for somebody to respond.
It's going to leach out.
Okay, who said that?
Scott's Bluff.
Scott's Bluff, thank you. It's going to leach out, exactly. And so this is where my crop perspective really comes in, but I still think we need to focus on things like this in urban management as well, which is nitrogen is going to leach out because it is not chemically attracted to the soil in any way. It's kind of like magnets that want to repel each other, and so it dissolves in water, and when we get excess rainfall that falls on that soil, it actually leaches it through the soil, and ends up in the groundwater. And we have a significant issue with that in parts of the state because of that simple fact. Nitrogen is a very hard nutrient to manage. And so that we have to kind of change the way we think when we do manage with nitrogen. And we'll talk about that as we keep going as well. Some typical ranges, just so you have some kind of reference or frame of reference to understand. I said clay is the only thing in organic matter that contributes to CEC. But your soil texture is composed of those three particles, sand, silt, and clay. And rarely are you going to find a soil that's 100% sand. It's going to have some organic matter in there, which contributes a little bit to that CEC. So that's why you see here at the top, a sand with 1 to 2% organic matter has a very, very low value of CEC. And as you add more clay into your soil, your CEC jumps way up. And humus, which is a form of organic matter, is loaded with CEC. Typical soils you'll see, though, fall in this range right here. I have seen soils this low. It's hydroponics, so if you do any type of hydroponic gardening, you're going to have little to no CEC, but in those cases, you don't care that much because you're constantly flushing the system and it's a self-contained system. You're not worried about leaching out. You're just maintaining a certain nutrient concentration. Okay. Transitioning to soil pH. Now, this is probably, in my opinion, for gardeners, this would be the #1 critical thing to know and to think about. Would you redefine CEC? Absolutely. Let me go back to it. CEC stands for cation exchange capacity. Cation meaning a positively charged ion. And so if you look at this diagram, you see magnesium and hydrogen. Those are salt ions. I'll refer to them as salts a lot of the time because fertilizer salts, which dissolve in water, they have a positive charge associated with them. Anions have negative charge, largely a minimal existence in soils. Cation exchange capacity holds on to cations. Does that help, Buffalo? Soil pH is probably the most critical thing for taking care of your nutrient issues in your soil. I would imagine that most of you who are gardening are turning over that soil a lot and putting in a lot of compost year after year. Compost is a complete fertilizer. It has every single nutrient in it. And so generally you're not limited in terms of nutrient content, absolute amount of nutrients, because you're adding so much into the system. But sometimes you could be minimizing the availability of the nutrients you're trying to add to the system. And what do I mean by that? pH governs a lot of the availability of a given nutrient. There's different chemical reactions. Some of them are called reduction oxidation reactions. Way too much information for this talk. But they are causing different swings in terms of if a nutrient is going to be available or not. It's dependent on this fact that pH is governing it. And so lower than 7 is considered acidic, and values higher than pH of 7 are considered basic, or you might hear the term alkaline. And we have tools at our disposal to either lower the pH or raise the pH. And a lot of that depends on the type of soil you're starting from, your parent material, the climate you exist in. So for example, Western Nebraska, which is more arid, would typically have more base cations, which tend to make the soil more basic. Those would be calcium, magnesium. It has an effect on the soil that raises the pH. Not only that, they have evaporation occurring more heavily out in the west, which tends to bring salts closer to the surface, thereby enhancing the change in pH. On the east, there's the opposite issue, where you have a lot more rainfall. You have leaching just by the sheer amount of force that water exerts. It can pull some of these nutrients slowly through the profile and create that E horizon, which we talked about at the beginning, and deposit those basic cations in that B horizon. So let me go back to that slide real quick. I think it will serve us well. Okay, so if you think about the process of soil developing over time, if you have a lot of rainfall, it's pulling down the basic nutrients or the basic cations, and they're depositing down here. So B horizons, if you've ever dealt with them, for example, a lot of urban soils have been stripped of the topsoil. This is really common in Omaha, or at least it was common in Lincoln and Omaha or bigger cities, where you'll have these housing developments come up. Companies will literally scrape off the topsoil and sell that, which you end up rebuying at the hardware store. But what's left is this mucky, thick, yellow-looking, a lot of people call it yellow clay, and it's the B horizon. And it's really basic compared to what topsoil was there, and it's really thick stuff because it's mostly been accumulated clay. Okay, so that's an example of how your topsoil can leach out basic cations, end up in a lower horizon, thereby leaving the top horizon more acidic. But in Western Nebraska, just the opposite is true, where the evaporation brings up to the surface those cations, and they stay in the topsoil, and it creates a more basic situation. So remember that fact, because when we do the final activity, we're going to come back to that. I don't know if I want to belabor this point too much, but if you're not familiar with the concept of pH at all, it's measuring how many hydrogen ions are in solution that exist between that and equilibrium with water. And each number change is a magnitude of 10. So that's why when you look at this diagram, when you lower your pH from 6 to 5, it changes, it goes from 10 to 100, 100 to 1,000. And so these are large, large changes. So just because it seems like there's very little difference between 6 and 5, actually it's a tremendous difference when you think about what's occurring in the soil. What influences soil pH? We talked about the climate, water, evaporation out west, CEC, believe it or not. Remember, I was drawing that diagram of how many positively charged cations can be stuck to that particle. Well, based on that, that's how many hydrogens it can hold on the particle versus how many are in the soil solution. Soil pH is not the measure of what's going on in the soil particle. It's measuring what's in that liquid soil solution. And that's the area that your soil or your plants are interacting with the soil. And so that's why we measure it, and that's why it's critical to get that right and in a range that's acceptable for the type of plant you're growing. So for example, every plant has kind of an ideal range of soil conditions it grows in terms of pH. So what would a typical plant that likes to have a more acidic soil or lower pH be? Blueberries. But typically, if you're not growing blueberries, we want to keep it in the range of like 6.7 to 7.2 pH if at all possible. And the reason I say that is because when you look at the relative availability of nutrients and where the most are available at a given time, we maximize it around that range. And so this is the sweet spot, not only for plant growth for the most part, but also for nutrients. And it's no coincidence that the plants and the soil evolved that way. It's a synergistic relationship there. Now, I chose this chart over the many hundreds that are available that you can look at for availability, because it also includes something that we rarely think about, which is the microorganisms. Those things are living in your soil too. And the soil for them is their house, it's their environment. And these things are vital for turning over nutrients and cycling. And so we need to make it hospitable to them as well. And fortunately, they need relatively similar conditions to what your plants. Now, from a crop perspective, the plant that comes to mind is soybean. But that's very similar to other legumes that you would grow in your garden, like peas or beans. And that is, if there's any type of symbiotic relationship rather between a bacteria that helps fix nitrogen and lives with the plant as the host, both of those conditions in the soil need to meet the needs of both the microbes and the plant that the microbes are basically symbiotic with. So does that make sense?